It's not my water. Here we go. So my name is John Althouse. I'm going to be talking about detection with Bro. And I work at Salesforce doing detection at Salesforce. So if you've never, one second, here's next. Can you give me next? There we go. All right, so right now you're probably thinking that I'm a professional programmer that likes to profile traffic with Bro and Broduction, and you're absolutely right. But Bro got its name because it's an Orwellian nod to how it's watching all the traffic that's happening on the network, and it logs all of that traffic. So it generates a ton of logs based on every session, every packet that it sees. So just a single connection can create 10, 20 Bro logs. And the first time you look at those logs, you're like, well, first, that's a lot of logs. But second, what's going on my network? Why is my Nest thermostat creating a reverse shell into it? Stuff like that. But that's how Bro works just out of the box, logging all the things. But what I want to talk about is how we can write detection on top of Bro using the programming language. And so my the first detection that I wrote for Bro, I was thinking about what adversaries do I want to detect with this first Bro script, right? And so you got your state-sponsored threat actors, your internet criminals, hacktivists, and then you have pen testers, red teamers, the guys that are normally speaking at security conferences, hacking all the things, dropping all the O-days and whatnot. And so I wanted to go after Metasploit, specifically Metasploit's randomly generated SSL certs, because every time you load up Metasploit, you do something over SSL, interpreter reverse HTTPS, or you browser auto own or all that stuff, and you want to do it over SSL. It randomly generates a brand new cert every time, which is really cool. You can't just use the cert for Intel, right? Interesting thing about this talk. I gave it a while ago at Nova Hackers, which is a local hacker group in Northern Virginia, and Mubix was doing his talk first. And if you know Mubix, he's doing this. He was hacking all the things, and he was exfilling all the data and getting all the passwords, and he's using interpreter over HTTPS, and it's encrypted, and you can't detect it. Boom! And then everyone applauded, standing ovation. He drops the mic. Hacking is sexy, right? And then I came up next, and it was perfect because then I could go, here's how you detect everything he just did. And that's how I wish every security conference was. You got the first guy is hacking all the things, dropping the 0 days and everything, and then the very next guy is here's how you detect everything they just did and prevent and whatnot. That would be perfect. Anyways, so here's how this went. So here's how Bro. This is what the Bro logs look like for the Metasploit randomly generated certs. You can tell it's obviously just completely random nonsense. Random.gov that definitely doesn't exist in the state of Wisconsin, country code US. And so looking at the Metasploit code on how it comes up with this randomly generated cert, you can see the country code is hard-coded to US, the state's random state, and then some random mixed case or random alpha 10 to 30 characters for the L and O fields, and then Sienna's random host name. So how does it come up with the random host name? It looks like it's just a random 10 plus 1 characters, then it adds a TLD, ComNet, or GovBiz, EDU at the end of that. And then for random state, it just has a list of all the US states, and I guess it just picks one at random. And then I was wondering, what is random text alpha? And here's the code for that. It's just uppercase characters and lowercase characters. So that's how the code works. And so the stuff in blue is what I think that I can generate a detection based off of. And again, this is what it looks like. So I was looking at the location field, right? The location field's supposed to be a US city, right? That's your city name. And then country code's hard-coded to US. So I was trying to figure out how do I write a regex string to detect random mixed case alpha? And so I wrote this really long, complicated regex, and it kind of works sometimes, but it was really taxing on the system. And then I came up with an epiphany, and I realized that I could just do this. Because the location field is a city name, and the country code's hard-coded to US, so it's a US city name, what US cities have lowercase characters followed by 2 or more uppercase characters? And the only thing I could think of was Washington, D.C., if you don't use a space, but then you just add that to your false positive list, and that's it. So this worked great, really great. In a 10,000 user environment, we're talking 1 false positive a month. It's awesome. So here's the bro code. And really all it is just looking for C equals EOS in the X509 data, and then that little regex there in the location field. That's basically it. So, and then the alert would look like this, and it's clearly obvious to any analyst that would look at this that it's a Metasploit cert or at least a randomly generated cert and whatnot. So, so I gave that talk at Nova Hackers, and not even a month later, this guy, hmore-r7, updates the Metasploit code on GitHub. And he says, so HD says, auto-generated SSL certs now match snake oil defaults. This change emulates the auto-generated snake oil certificate of Ubuntu 14.04. The main changes include moving to 2048-bit RSA, SHA-256, single name CN for subject and issuer, and the removal of all those other certificate extensions. So, all right, let's do this. So here's the Metasploit code, and really interesting is right there at the top. The valid from is between, for the certificate, it's valid for 10 years, but the valid from is from a random point in time between now and 3 years ago. So I thought that was really interesting. I was actually going to use that for my next iteration of detection, but he beat me to it. And then the CN is random text alpha lower, 2 to 10 characters, and the subject and issuer are the same, and it's signed SHA-256. So here's what it looks like in Bro, and it's very, very simple in comparison to what it used to look like. But again, he was trying to emulate the snake oil cert, and if you don't know what the snake oil cert is, it's just when you have Ubuntu and you ask Ubuntu to make an SSL cert for you, it generates one based on your host name and stuff like that. And so that's what he was trying to emulate. And we can see the differences here. Everything is red is the same though. The issuer contains a CN only. The issuer and subject are the same. They're both 2048-bit keys, and they're both valid for 10 years. Though the snake oil cert is starting now as soon as you make it, and the Metasploit 1 randomizes that. But here are the main differences. The snake oil cert is SHA-1. The signature algorithm is usually SHA-1, at least for now. Maybe it'll change. But the Metasploit cert is hard-coded to always be SHA-256. And the CN for the snake oil cert is hostname.domain. Notice the uppercase characters and the period in there. And the Metasploit cert is just 2 to 10 characters of lowercase mixed, or lowercase just alpha, right? So that is what my logic is for detection. And here's the bro code to detect it. It's really simple. Everything in red is just tuning, and then the 3 lines in blue are the actual detection mechanisms. So up top in red, we're just making sure that the responding host and the session is not inside of our network. So we just filter that out. And then we're making sure that there is a subject and an issuer inside the cert, and that the cert is not in our false positive list. You build a small false positive list. And then the detection logic is just making sure the subject and the issuer are the same, that the subject is just CN equals, and then lowercase characters 2 to 10 of them, and then that's it. That's the whole cert subject. And that it's signed with SHA-256. And this works great. Again, we're talking like 1 false positive a month. After you filter out, of course, your first like week or 2 of false positives. So you just run this for a week or 2, don't alert the analyst, and get all your false positives, add that to your false positive list. But then after that, you're looking at about 1 a month, which is, for an analyst, that's gold. So again, just 3 lines of bro code, and you're detecting everything related to Metasploit that's over SSL with its default randomly generated SSL cert. So pretty awesome. So moving on to something else, file exfil detection, regardless of the encryption or the protocol. This is great. This was all based off a script that was originally developed by Bob Rotstead at Reservoir Labs. So thanks to them, this is awesome. And I've just modified it to provide a little bit more detail to be more useful for the analysts. But here's how it works. So normal outbound traffic looks exactly like this very scientific graph here. But a file transfer outbound looks like this, right? Clear as day. So how do you detect that? Well, and this is what Bob came up with at Reservoir Labs, you just threshold the byte count and the byte rate, and that's how you detect the file transfer being sent outbound. And so that's how the script works, and it logs every time there's a file transfer outbound with the source destination byte sent. But what I added was the service, the domain if it was available, the SSL cert if it was available, and I added those to the bro logs that it's generating for all of these file exfils. And how I did that, the code's on the right side. So at the top of the bro script, you would add what you wanted to add, like host, subject, and you just say those to log those, but they're optional. And then at the bottom, further on down in the bro script, I would say for the subject, for example, if the connection is SSL, then the subject equals C SSL subject. Or if the connection is HTTP, then host equals C HTTP host. So on and so forth, and you can add all these things into the bro logs just by adding those to the bro script. So you may be thinking at this point, oh, here's how I'll alert. I can alert on large file transfers outbound saying, if the source is RFC 1918, it's inside my network, and the destination is not inside my network, and the total amount of bytes sent is over like 250 megabytes or something, and for tuning, say the SSL cert does not equal box.com, then alert. But no, remember that bro is logging every time there is a file transfer out of the network, regardless of if the connection's been closed or not. So even if, say for example, you make an SSH session out of the network, right? And you start sending files. Well, as soon as your first file is done being sent, bro generates a log saying where it went and all those details and exactly how large that file was. Even if that SSH session is still open. And the next file that's sent, it'll generate another log for that one, so on and so forth. So it basically looks like this. I've condensed it down so that it's readable. But notice how for box drop, as an example, the destination IP changes, but the cert's the same, right? So what you can do is you can aggregate on your logging platform. This is a Splunk as an example, but you count all those logs as a file count. And then you can sum the bytes sent as your total amount of bytes sent, and you aggregate based on source IP, domain, certificate, subject, service protocol, etc. And then this is something that really bothers me. I hate seeing strings that are for bytes, and if it's like gigabytes, I have to do that thing where I do it with no commas from 123 kilobytes, 123 megabytes. I hate that. So just do the world a favor, take your bytes total and divide it by 1024 twice to just make the world a better place. But the end result is a valuable log that you can hand to the analyst, just this nice, perfectly packaged thing that says the source IP connected to these destination IPs over port 443 in this example. The service was HTTPS, so because it was HTTPS, bro logged the destination certificate. And that's what we're correlating on. So we know that all of these connections were to boxdrop.com. And then bro can verify, has the ability to verify whether a certificate is valid. And then we can show that it transferred 512 files totaling 2 gigabytes. And so this is just a really neat, easily digestible package for any analyst to look at and make a determination on what to do next, right? So for more fun, you could send all of these exfil logs to a user behavioral analytics engine, get some machine learning awesomeness on it, but that's that. Moving on. Reverse SSH shells, and credit goes to W's epiphany. So for reverse SSH shells, how it works is an exploit script or something on an internal host will run something like this, binding a local port, and then SSHing out to, let's say, Amazon. And then on your evil Amazon C2 server, we'll just SSH to that local port. That's a reverse SSH shell. If you need diagrams like I do, here's a diagram. Your system inside your corporate network, it's infected, or an evil script runs on it or something like that. It binds a local port and then SSHs out to this evil AWS C2 server as an example. And then the threat actor on that AWS server SSHs back over that existing SSH session onto the internal host, allowing them to send commands as if they were just typing at that console inside the corporate network, bypassing the firewall, all that stuff. That's what we're trying to detect. So for a normal SSH shell, every time you press a key, a packet is sent and then received. As you're typing on your SSH shell, as you're typing, you're seeing characters come up in your terminal, right? And you know that your terminal has died when you're pressing characters and you're not seeing anything come up, and you're like, crap. That's because the server's not sending the characters back to your client. So it looks like this. And each of these characters are padded. So in Linux, they're padded to 48 bytes. With Macs, they're padded to 42 bytes. So Linux, as an example, client to server, you send the letter P, right? It sends 48 bytes to the server. Server responds, letter P is padded 48 bytes back to the client, so on and so forth. But with the reverse SSH shell, and this was W's epiphany, it's double padded because it's an SSH shell over an SSH shell, right? And it's going from, instead of client to server, it's from server to client because the typing is happening on the C2 host. 96 bytes back, right? And then the client responds 96 bytes, so on and so forth. So, well, there you go. There's our detection, right? 96-byte packets. But no, that happens all the time. So we need to look at each packet individually, one after the other, to identify typing. So initial bro script was looking for first packet 96 bytes, next packet 96 bytes, a couple of times over, and then alert. But that's forward SSH shells also look like that all the time. So let's get more granular with bro. My next iteration, I was looking for from server to client 96 bytes, and then from client to server 96 bytes. At least a couple times over, but still just false positives all over the place. Pretty useless. But then I realized the client is going to be creating is going to be responding to the commands, right? So server to client 96 bytes, client to server 96 bytes, a couple times over, and then the response from the client is obviously going to be longer over 96 bytes because it's going to be a string of characters. It's going to be responding with whatever the threat actor was typing in. So on Moloch, it looks like this. And by the way, if you don't know what Moloch is, it's this awesome open source full PCAP tool. You can find out more at molo.ch. Anyways, here's what it looks like on Moloch. The right side is the server, the left side is the client, and these are all 96-byte packets. So the server types P, W, it goes back and forth, and then on the server side, he presses enter. That's 96 bytes going to the client. The client responds with the path for PWD, and that's, in this instance, 208 characters, or 208 bytes, and that's how we detect. And it works great. And here's the bro script for doing that, and essentially how this bro script works is, and this is awesome, Vlad, one of the main bro devs, came up with this event SSH encrypted packet. So this is not very intensive at all. It used to be. But so the way this works is we're saying if the originator of the connection is false, meaning that this is coming from the server, and the length of the packet is 96 bytes, and then we're creating a counter. We're calling it, in this instance, it's called LSH_cons, but you can name it whatever, right? If the counter is 0, meaning this hasn't happened before, then increase the counter to 1. And then we're looking at the next byte, right? And if the next byte is from the originator, therefore the client, and it's 96 bytes, and we're at counter of 1, then increase the counter again, so on and so forth. Until we got a couple characters typed, and then finally we're just looking for the client to respond greater than 96 bytes, and then it fires the alert. So again, this works great. We're as far as false positives go, one a week, every other week. It's very low, very easy for analysts to digest and analyze. And if anything, every single time this fires, the connection is totally worth investigating and trying to figure out what exactly are you doing here. So why do we do this on Bro? Because snort-based NIDs do not have the next granular next packet analysis. You can't tell snort, this happens on this packet, and then the next packet needs to look like this. Snort doesn't have the ability to do that. But the Bro scripting language gives us that power to look at each individual packet one after the other. I also need to mention, because there's multiple variations of SSH clients and servers, multiple Bro scripts were needed to cover all of the different operating systems that were in our environment. But it was only about 4 scripts, and it covered pretty much everything. So in conclusion, just showing what's possible with Bro, hopefully changing your perspective on what can be detected on the wire and how. But the main thing I want you to remember is if you can see the evil in packet data, if you're looking at a PCAP and you can go, I know what that is, that's bad, then you can definitely write a Bro script to detect it. So shout outs to these guys. They taught me everything I know, and that's it. Any questions? Yes. So with any Bro script, there's always a performance penalty, though very small. There's not a lot of SSH traffic out of our network, and it's only going to be doing that analysis when there is an SSH session. And again, it's basically one cycle per packet going through it. It's not anything worth worrying about. So benefits outweigh the cost. Yeah.
But when you're counting files, if you have a long persistent connection and that log rolls, would that count as a new file? As opposed to, let's say you transfer a huge file.
Oh, okay, yeah.
And effectively it shows up in 3 different Bro logs because it took a long time to transfer. Would that show up as 3 files?
Well, no. So Bro will watch state for a long time. So it will start counting, and you're sending like a huge, 30 gigs, 50 gigs, whatever. A huge file, and let's say it takes a long period of time. As long as you're not restarting your Bro server, it will just keep watching it and keep counting until it ends, and then it will log it as that. So, yeah. Do you have a question?
I'm just curious, for your Bro sensor itself, did you guys build your own or open source solution?
Yeah, we just built our own, buy really good hardware. Important thing to note about Bro is that it really likes high-end CPUs per core performance versus lots of cores. So it's better to get something like a 12 or 16 core, 2 CPUs together that have really good per core performance versus something like 32 cores where each core is just a mediocre 2 gigahertz thing, So so we built our own. It's not too bad.
How well does it do with
So which ones?
So like the reverse shell, you get false positives,
No. Because we're looking at, each packet one after the other, looking for 96 bytes, going in the directions that they're going. And we're looking at this for a couple iterations, and then we look for a response from the client to the server. It's just extremely rare for something like that to happen over, SFTP or something like that. It's not impossible. Again, like I said, we do have some false positives, but it's very rare, and every time there is a false positive, usually the connection is worth investigating and asking the user, what exactly were you doing here? So, is that it? Cool, thanks.